If I asked you to imagine the biggest and most dangerous challenge of a crewed mission to Mars, what would come to mind? You would probably picture the outbound journey itself. A lonely spacecraft crossing the dark void of space for months on end, facing the unknown, radiation, and the lack of gravity. The journey seems like the great epic, the ultimate test of courage and technology. But what if I told you that this perception, although understandable, is fundamentally incomplete? The truth is that the real endurance test of a Mars mission, the longest, riskiest, and most psychologically demanding part, only begins after the astronauts plant their boots in the red dust. Because of a peculiarity of orbital mechanics, a quirk of the cosmic dance between our worlds. The most efficient and safest strategy with the technology we have today forces explorers to remain on the red planet longer than they would like. Only after a long wait can they even think about aligning their spacecraft for the journey back home. To understand an interplanetary trip, the first thing we need to do is abandon the idea of drawing a straight line from one point to another. Space is not a static map. It is a dynamic and perpetual ballet, and the reality of our journey is a celestial dance. Think of Earth and Mars as two race cars on concentric oval tracks around the sun. Earth is on the inner track, shorter and therefore much faster. Mars is on the outer track, longer and slower. Earth completes one orbit around the sun in 365 days, while Mars, our slower neighbor, takes a long 687 days to do the same. This difference in speed means that the distance between the two planets is constantly changing. At certain moments, during an event called opposition, the planets line up on the same side of the sun, and the distance between them shrinks to just 55 million kilometers. At other times, they are on completely opposite sides of the sun, in a configuration known as conjunction, separated by a maximum distance of more than 400 million kilometers. Our intuitive logic would say, so we just launch the spacecraft when they are closest, right? That would be ideal, but celestial physics is counterintuitive. Launching a spacecraft directly toward Mars during opposition would be like trying to jump from a car moving at high speed to another that is moving more slowly, but is already far ahead. To catch up with Mars, the spacecraft would need an enormous initial acceleration, and upon arrival, it would need to brake even more violently to avoid overshooting the target. The amount of fuel required for these brute force acceleration and deceleration maneuvers would make the mission impractical with current propulsion technology. Instead, space engineers use a much more elegant and efficient trajectory, known as a Hohmann transfer orbit. We launch the spacecraft from Earth not straight toward Mars, but onto a wider elliptical path around the sun. The spacecraft coasts for months, using the sun's gravity to guide it, until its trajectory intersects Mars' orbit at the exact point where the planet itself will be arriving. It is the most economical way to travel, maximizing fuel efficiency. The problem is that this perfect orbital configuration, the so-called launch window, is a rare event. It only happens every 26 months, when Earth is in the right position to catch Mars in the most efficient way. If a mission misses this window, for any reason at all, it has to be postponed. The team must wait more than 2 years for the next opportunity. It is this slow and unchangeable rhythm of the planets that dictates the entire mission schedule. Using chemical propulsion rockets, which are the backbone of space exploration today, the trip to Mars takes, on average, 6 to 9 months. To give you an idea, NASA's robotic missions, such as the Curiosity and Perseverance rovers, took about 7 months to cross the abyss between worlds. During all this time, the astronauts live in a state of extreme confinement. Imagine your entire world reduced to the volume of a small apartment, shared with a handful of colleagues, for a period equivalent to 3 seasons on Earth. And this journey is far from a smooth crossing. The first and most treacherous danger is cosmic radiation. Outside the protective bubble of Earth's magnetic field, the crew is constantly bombarded by high-energy particles, both from our own sun and from distant galactic sources, such as supernovae. Prolonged exposure significantly increases long-term health risks. Then come the insidious effects of microgravity on the human body. Our bodies evolved under the constant pull of Earth's gravity. Without it, the body begins to adapt in harmful ways. Muscles, especially those in the legs and back that no longer need to support weight, begin to atrophy. Bones lose density at an alarming rate as the body interprets that the skeletal structure is no longer necessary. The cardiovascular system weakens, and even vision can be permanently affected due to changes in fluid pressure in the head. And of course, there is the immense psychological challenge, the isolation, the monotony, and the constant awareness that your home is just a tiny blue dot, millions and millions of kilometers away. Any help, in case of an emergency, is months of travel away. After nearly 9 months of trials, they finally arrive. The landing sequence, a risky and complex process, is a success. Humanity is on Mars. The world celebrates. You might think the worst is over, that the hardest part of the mission has been overcome. But in reality, the challenge of survival is only just beginning. They are on Mars. The flag is planted, the first soil samples are collected, the first steps are taken on a new world. The euphoria is immense. But after a few weeks of initial exploration, the inevitable question arises, okay, now what? Why don't we refuel and go back home? And here lies the crucial point of the entire mission, the paradox of traveling to Mars. They cannot simply pack up and return as we did on the moon, not in the most efficient and safest way, at least. Remember our dance of the planets. At the moment the astronaut spacecraft arrived at Mars, Earth did not stay put. It continued its fast journey on the inner track. Seen from the Martian surface, the astronauts would watch Earth rapidly pulling away. Trying to launch a return vehicle immediately would be like trying to swim against a powerful cosmic current. It would require such a monumental amount of energy and fuel that it would be necessary to bring a gigantic launch rocket all the way to Mars, something that is far beyond our current logistical capabilities. Of course, there are theoretical proposals for short-stay missions, in which the time spent on Mars would be only 30 to 90 days. The problem is that, to enable such a quick return, the mission would have to use extremely high-energy trajectories, both on the way there and on the way back. This would require much more powerful rockets and much more fuel, drastically increasing cost and complexity. The alternative would be a much longer return journey, which would cancel out the benefit of staying only a short time on the planet, exposing the astronauts to more radiation and microgravity. That is why the most studied, most efficient, and most likely mission architecture to be executed is the long-stay mission. In this scenario, the only viable option is to wait. To patiently wait for the planets to continue their orbits until Earth and Mars realign into a new, favorable position, opening an ideal launch window for the return, and this wait is anything but short. For this orbital geometry to occur, astronauts must remain on the surface of Mars for about 500 days. Yes, you heard that right, 500 days, almost 18 months. After a journey of nearly 9 months, the crew must establish a base, live, and work on Mars for a year and a half before even beginning the long trip back. This is by far the longest and potentially the most dangerous phase of the entire mission. If anything goes wrong on the surface of the red planet, game over. Spending 500 days on Mars is a continuous survival test, where the margin for error is zero. The dangers are not occasional, they are the permanent state of the environment. First, radiation, which is now a constant companion. Mars's atmosphere is about 150 times thinner than Earth's, and the planet has no global magnetic field to deflect cosmic particles. This means the surface is bombarded by a level of radiation that would be unsustainable for human life in the long term. Astronaut habitats would need heavy shielding, perhaps partially buried under Martian soil, to use the regolith itself as a shield. Then there is the Martian environment itself. The atmosphere is composed of 95% carbon dioxide, completely toxic to us. Any catastrophic failure in the habitat's life support system, or a rupture in a spacesuit during an extravehicular activity, would be fatal within minutes. Atmospheric pressure is so low, less than 1% of Earth's, that without the protection of a pressurized suit, exposed bodily fluids, such as saliva and tears, would begin to boil and vaporize, even in freezing temperatures. It is a brutal reality where survival depends entirely on the perfection and resilience of technology. And of course, there are the famous and feared Martian dust storms. They are not localized dust devils. They can grow into events that engulf the entire planet, blocking sunlight for weeks at a time. This fine and abrasive dust can infiltrate mechanisms, damage scientific equipment, and most critically, cover solar panels, cutting off the base's main source of energy. To mitigate this existential risk, most serious NASA mission proposals already consider the use of small nuclear fission reactors as the primary power source, ensuring the base keeps running and the astronauts stay alive, even during the darkest storm. Finally, perhaps the greatest challenge of all, the human factor. On Mars, Earth is not a visible planet in the sky. It is just another bright star, a point of light. Communication with mission control has a delay ranging from 4 to 22 minutes each way. This means a question sent to Earth can take up to 44 minutes to receive a response. Real-time conversations are impossible. Imagine a medical emergency or a critical equipment failure. The crew is on its own. They are their own doctors, engineers, and first responders. The mental resilience required to endure this deep isolation, constant stress, and monotony, knowing that help is months away, would be pushed to the absolute limit. After approximately 500 long and grueling days on the Martian surface, celestial mechanics finally cooperate. The dance of the planets aligns Earth and Mars into the ideal configuration. The launch window for the return opens. The crew boards their ascent vehicle, lifts off from the Martian surface, docks with the spacecraft waiting in orbit, and begins the final and bittersweet stage of the journey. The trip back home is, in essence, a repeat of the outbound journey. Another 6 to 9 months of confinement, once again facing the dangers of deep space radiation and the debilitating effects of microgravity on their bodies, which have already been weakened by the long stay in partial gravity. So, let's do the math and put together the complete timeline of this epic mission in its most likely architecture. First, there are about 7 to 9 months of travel to reach Mars. Then, a planned wait of about 18 months, or 500 days, living and working on the Martian surface. And finally, another 7 to 9 months for the journey back to Earth. Adding everything up, we arrive at a total mission duration ranging from 34 to 36 months. That's right, almost 3 years. A mission to Mars is not a simple trip. It is a life commitment, a voluntary exile of nearly 1,000 days. That completely changes our perspective, doesn't it? Reaching Mars is, without a doubt, a monumental engineering feat. But the true journey, the real test, is a marathon of patience, psychological resilience, and human endurance. So, what do you think is the biggest obstacle? The technology of our rockets, or the strength of the human mind and body to withstand such an ordeal? For now, with the technology we have in hand, conquering Mars does not depend only on the speed of our spacecraft, but fundamentally on our ability to wait. The true frontier is not just distance, but time. Would you board a spacecraft on a 3-year journey into the unknown, even knowing that there is a significant chance of never returning? If you enjoyed the video, leave a like, subscribe, and share. Thank you for watching until the end. See you next time.